The broadcast is now starting. All attendees are in listen-only mode.
So, welcome everyone. I hope you are all safe and healthy. I'm Javier Miranda, Vice President of the SPWLA Houston chapter and your host today. I'm really happy to see a high participation for this event. Actually, we had some minor technical difficulties that were sorted out thanks to our great VP of Education, COVID-19 has challenged our industry in many ways, but at the same time has triggered several opportunities and new forms to interact and reach out to you as a society. I would like to thank you today for participating in our June webinar about petrophysical evaluation in the Vaca Muerta formation in Argentina, a very important unconventional shale play. Uh, Today, this talk will be given by Alberto Ortiz. Thanks, Alberto, for volunteering and making this possible. I would also like to thank YPF, SA, and the Goliera Magnoto for their support to Alberto and myself, respectively, to organize this webinar. This event is supported by Petromar, a neighbors company. Thanks to Manfred Frass and Andy Duncan for their support. Thanks also to Katerina Yaret, SPWLA Vice President of Education, for the help on setting up this webinar. And without further announcements, I will read Alberto's bio, followed by his presentation. Then we will have a Q&A session at the end. Please type in your questions. I will read them for Alberto, and he will address them at the end. So Alberto Ortiz is a principal petrophysicist of YPF SA Argentina. He graduated in geology at the University of Cordoba. He started in Total Austral in 1997, and 3 years later, he joined Schlumberger as a petrophysicist based in Argentina and Brazil, focused information evaluation using waterline and logging while drilling measurements. In 2011, he joined YPF in Buenos Aires, Argentina, and since 2013, he's a member of the Unconventional Shale Play Reservoir Characterization team. So without further announcement, let's go to Alberto.
Okay. Good afternoon, everybody. Could you hear me, Javier?
Yeah, I can hear you.
Okay, perfect. Thank you very much, Javier, Katarina, and all SPWLA chapter Houston to invite me to make this presentation. I actually had the opportunity to make this presentation during the last 2 years in different locations around the world in a great community of SPWLA. So first of all, I will start talking about making a brief introduction about where Vaca Muerta is. Vaca Muerta is located in South America, more precisely in Argentina, West Argentina, in what we call the Neuquén Basin. It's a basin located in West Argentina. Vaca Muerta is a marine formation and is being one of the main, if not the main, unconventional development outside United States for shale plays. So basically what I want to show here with this slide is how compares Vaca Muerta with other reservoirs, shale plays in United States. Basically, Vaca Muerta was deposited during the late Jurassic and early Cretaceous ages. The prospectable area is quite big, 30,000 square kilometers. But the two things I want to mention about Vaca Muerta that highlights compared to some other reservoirs in the world is the relatively high porosity. Here we have a porosity of a medium values from 4 to 12 PU, but actually it can go even up to 12 PU. And also the kerogen content. The kerogen content is quite high. It could be even 15% in weight percent, so that means that 30% of the total volume of the rock it could represent. It could be represented by kerogen. So the maturity of Vaca Muerta covers a wide range of maturity from immature oil to dry gas window, and it's a kerogen type 2, a type 2S. The thickness is another thing that I want to highlight. It's quite thick. is from 200 meters at the border of the basin, and it could go up to 800 meters at the center of the basin. So in order to make a summary about what we have learned, I will start talking about the heterogeneity of the rock that we started to look at, into it a couple of years ago. And then I will go through the analysis, the typical analysis that we do for unconventional rocks, looking for mineralogy. Then I will show something about the maturity, water saturation, pore system characterization, and finally what we are doing now about data analytics. So Vaca Muerta, as I said before, is a marine formation. It was sedimented during the late Jurassic, and because of that, it was sedimented in a platform, carbonate platform. And here, what we could see in this slide is the 3 vertical wells located 30 kilometers away from the other one, with the typical passé crossover, the resistivity and the sonic. So we can define Vaca Muerta, the top and the base of Vaca Muerta, by the passé crossover. And also we can see in this yellow shaded area, the thickness of Vaca Muerta in different positions from southeast to northwest. So we can define here the top of Vaca Muerta, and we can see how the thickness is increasing from southeast to northwest. But because Vaca Muerta is marine sedimentation and is located in a different position of the platform, we could see here in the seismic line the clinoforms from the Quintuco, which is the formation underlying Vaca Muerta, and also Vaca Muerta progradation towards the northwest. That means that Vaca Muerta, it could be located in different positions on the carbonate platform, and because of that, the mineralogy and different properties will vary at the seismic scale. This is one of the things that we need to take into account when we analyze Vaca Muerta. It depends where we are. It depends where we look into. It will vary a lot at the seismic scale. Here at the bottom, we can see that we have 3 vertical wells. With the passé crossover, we can see the gamma ray increasing through the bottom by the increase of TOC content, and different electrophases, which are represented in this track with different colors, that shows the variability of the different rock types across a different position of those 3 wells. So this was one of the first things that we observed when we started to work in Vaca Muerta, is when we are saying Vaca Muerta, we are not saying only one unique type of rock. It covers a wide range of different rock type at the seismic scale. But then, okay. We went to the outcrops to observe as well how Vaca Muerta is in a smaller scale. Here we have a picture of 2 outcrops located in the west zone of the Neuquén Basin, close to the Andean. And here we can see the black shales interbedded with marls or layers rich in carbonate, more or less 1 meter thick. Those one, it could be resolved by the electrical logging, perhaps at a very high resolution mode. But here we have another example of Vaca Muerta from the lower Vaca Muerta, where we can see also some other levels of heterogeneity, like these lines, white lines that corresponds to what we call beef. Actually are calcite veins, and also some concretion. So there is heterogeneity at different scale levels, and this we need to took that into account when we evaluate the Vaca Muerta by logs. If you use standard resolution logs like neutron density or even sonic logs, we won't be able to resolve those layers from the bottom images. We will have some troubles to resolve this layer on the upper image. So we went into the high resolution logs in order to try to resolve some of those layers and that will help us to characterize the formation in a smaller scale. Here we have typical well logs for Vaca Muerta. We have the borehole images, the gamma ray, the resistivity from the induction logging, and also the resistivity for borehole images. And then we have the standard resolution logs in black curves and the high resolution logs in red. We can see that the high resolution is capable to resolve more layers compared to the standard resolution because of the high heterogeneity of the Vaca Muerta. And then what we did was to create some clusters with the standard resolution logs on the right and with the high resolution logs. We could see also the clusterization is showing or reflecting the highly heterogeneous or the thin layers presented in Vaca Muerta. But then what we will try to do was to obtain TSI curve from the scratch test, synthetic TSI, and compare with the actual TSI measured at the core. On this track, we can see the comparison between the standard resolution logs and the TSI, and we could see that some of the thin layers are not being resolved by using the standard resolution logs. We just could resolve that by creating a synthetic TSI cube with a high resolution log. So basically, that heterogeneity has to be taken into account with the logs, and it helps to when we are talking and when we are creating the geomechanical model of Vaca Muerta. Then we went to the mineralogy. We passed from different petrophysical models. This is a final petrophysical model, or I would say scenario that we use in order to characterize Vaca Muerta. It contains 9 different minerals. It contains kerogen, clay water, clay bank water, what we call pore water or IP water, 2 different hydrocarbons, light and heavy hydrocarbons. Basically, what we use in order to characterize from the mineralogy is to use a nuclear spectroscopy from the logs side, but also we use XRD and XRF from the core. We calibrate with XRD and XRF our mineralogical model into the petrophysical model, and then we use nuclear spectroscopy to perform the proper upscaling with the logs. We also use DRIS and FTIR from the core in order to characterize mineralogy and use a checkpoint for XRD and XRF. So here we have 2 wells of Vaca Muerta, one located in a shale gas window and another one located in a shale oil window. We could see on this track, first of all, we could see the thickness of Vaca Muerta, in this case more or less 200 meters thick. And also we could see the mineralogy of Vaca Muerta. It's not purely represented by clay. Clay actually do not represent the majority of the mineralogy in the rock. It only represents 20–25% of the total volume of the rock. It's also Vaca Muerta represented by quartz and calcite as the main minerals, and then we have subordinated some portions of pyrite, anhydrite, or even ankerite. Here we can see as well the heterogeneity on the mineralogy. In the well located in the left, we could see that the calcareous beds are not representing a big portion of the rock, but in the well located at the right, we could see that the calcite represents more or less 70–80% of the rock. So mineralogy it's an important input for the petrophysical model, and it's an important aspect to observe when we define and when we characterize Vaca Muerta. Then we went for porosity. which is quite difficult sometimes to define. We need to pass through to think about what we consider as porosity in this kind of reservoir. So basically, we come up with a conclusion that we will include as porosity heavy hydrocarbon, bitumen. We will include, of course, clay-bound water, kind of a pore water, and which data we're going to use in order to characterize the porosity. Our main, I would say, electrical logging suite in order to characterize porosity is the NMR, acquired in a standard T2 distribution, but also we use density neutron, and of course, the mineralogy coming from the nuclear spectroscopy. From the rock, we use a TRA, which is a tight rock analysis. It's a typical retort, and combine it in twin samples with the GRI, which is basically solvent extraction porosity combined with the gas field porosity, both techniques from the core. Then we define from that what we consider is total porosity and what we consider as effective porosity. Effective porosity is just total porosity subtracting the clay-bound water. Here we have a well. We have the gamma ray increasing through the bottom of Vaca Muerta, the typical Passé crossover showing an increase of TOC content, and also the TOC content coming from nuclear spectroscopy. On this track, we can observe some interesting features. The first one is the total porosity obtained from the petrophysical model, which is the red curve, and the total porosity from NMR. At this level of maturity, both are mostly the same. So that means that the NMR porosity is almost the total porosity of the rock, or interpreted total porosity of the rock. But when we compare the total porosity with the core data, we can observe some differences. The black dot points represents the porosity from GRA, which actually represent the solvent extraction porosity plus gas field porosity, and the blue dots represent the retort-based porosity, which are actually lower compared to the GRI porosity. So some of the questions come up: why the differences between the two methods? So we started to think that the effect of bitumen, or the heavy oil component, it could be affecting the porosity from the retort and not the GRI porosity. So basically, we come up with a conclusion that the difference between the two methods is because the bitumen content, and in case of running a logs, or in case of calibrating our porosity in a well located in a shale oil, we know we must use the solvent extraction porosity instead of retort. Then we went for maturity. Maturity is quite complex to define. In Vaca Muerta, I think in any shale plane in the world, we have many different ways to access maturity, or the maturity of the rock. The most frequently used in our case is the vitrine reflectance, but the sedimentation environment doesn't help us to obtain very accurate values of vitrine reflectance. So we also use a hydrogen index or Tmax from pyrolysis. But also we are exploring different other maturity indicators like a drift or like an even RAMAN spectroscopy. The idea behind this is just observe the variation of the maturity on the solid part of the organic matter, but also from the liquid. Some techniques are sensitive to the solid part, some others are sensitive to the liquids. So here we have a study done in Vaca Muerta showing the variability or the variation of some properties of the KEROGEN as a function of maturity, which is a very important input for our petrophysical model. Basically, we were capable to isolate KEROGEN and measure some properties. And we could observe that the atomic hydrogen carbon content values as a function of maturity. Also, the hydrogen index varies as a function of maturity, and finally, the density of the kerogen varies as maturity. So this is an important point that when we consider maturity in Vaca Muerta, mainly because what I said before, Vaca Muerta contains a very high TOC. It could represent between 20 and 30% of the total volume of the rock. So this parameter of the density, kerogen density, is an important input in our petrophysical model in order to calibrate all the electrical logging and our mineral solver. Here we can see as well the differences, as I mentioned before, between the two methods that we use for core analysis. On the x-axis, we can see the extracted oil by the DIN-STARK, or by solvent extraction, and the y-axis we can see the amount of oil obtained from heating the rock or by the retort analysis. And we can see the data from two wells located at two different maturity windows. The first one is the green well, which shows that the DIN-STARK method is showing an increase of oil content compared to the twin sample obtained oil obtained from retort. In the case of the dry gas window, that difference is smaller, the difference compared to the line 1-to-1. That difference is smaller, but still there is some difference, or at least the DIN-STARK is capable to measure or to obtain more hydrocarbon compared to the retort. So the difference between the line 1-to-1 in the shale oil window, we presumably think that is because the bitumen content or the heavy hydrocarbon, but we still don't have a clear idea why we still have that difference in wells located in the dry gas window. Some other way that we use to characterize the bitumen content of Vaca Muerta is by using T1, T2 maps from NMR. We collect these maps at every single depth of NMR acquisition in vertical wells, and then we apply what we call a blind source separation technique, which actually divides the signal of T1, T2 in different kind of spaces or bubbles, and then we're trying to resolve those volumes, trying to give some meaning of the volume in the rock space. Basically, what we think is that the bitumen contains a very high T1, T2 ratio. By doing that, we are capable to characterize the bitumen, and then we characterize the bitumen, the volume of bitumen across different maturity windows, and we have started to observe that wells located at the very high maturity windows contains less bitumen or less volume of bitumen by using T1, T2. So the heavy oil components are also being capable to be measured by the T1, T2 or at every single depth in vertical wells. This graph at the right shows a median value of the lower Vaca Muerta in terms of bitumen content. Then we explored the possibility to use a RAMAN maturity, which is a new technique to measure the maturity of the rock by looking at the difference of these two peaks. These are the results of the RAMAN maturity in a vertical well, 200 meters thick Vaca Muerta, and we were capable to observe some variability of the results. We are still not sure if this related to the uncertainty of the measurement itself, but what we can observe is that the trend from the top to the bottom is showing that there is an increase of maturity towards the bottom of Vaca Muerta, which mainly I will say is in line with what we think is actually happening, because the total thickness of Vaca Muerta we will expect have lighter hydrocarbons and more mature rock at the bottom compared to the top. The good thing from the RAMAN maturity is that not human-dependent interpretation. It's purely by the convolution of those two peaks. This was a problem that we have with the vitrine reflectant. Is more related to who is interpreting the data, and when we choose different labs, the bias that we could generate that in our maps and maturity indicators. Another way that we access the maturity is by doing a maturity inversion with electrical logs. This was a paper published by Mosset al. 2016. I'm co-author on that paper, and the paper is based on the variability of some properties of the rock as a function of maturity, like a kerogen and like a hydrocarbon. So basically, if we are in an open system, the hydrogen index of hydrocarbon and kerogen will tend to decrease as a function of maturity. So decrease the hydrogen index when we have a rock at high maturity. But also something different happened with the kerogen density, carbon index, and hydrocarbon density and carbon index of hydrocarbon. So by doing an inversion with electrical logs and assuming this background of changes in the hydrocarbon and dense kerogen, we are capable to characterize the maturity of the rock by looking, but making this inversion. Here we have two wells. The well located in the left is a shale gas well. The well located in the right is a shale oil well. We could see also that the neutron and density crossover, it followed the same behavior as a typical conventional reservoir. We have a crossover of neutron density in a shale gas well, and we do not observe that crossover in a shale oil well, which is basically one of the things that we observe and started to think about making this inversion with electrical logging. In this track, we can observe in orange the final vitrine reflectance, synthetic vitrine reflectance obtained by this electrical logging inversion, and we can observe clearly that the inversion was capable to define the shale oil well, and also was capable to define properly the vitrine reflectance on the shale oil well. And also we can see the variability of some properties of kerogen and hydrocarbon across different intervals. We can observe here in the shale oil well how the bottom of Vaca Muerta is more mature compared to the upper zone of Vaca Muerta, in the same way that we observe the Raman spectroscopy results. So this technique is very helpful to understand and characterize the maturity of Vaca Muerta across different maturity windows, and also in the vertical direction, taking the advantage of the very high porosity and the very high kerogen content of Vaca Muerta that represents more or less 30% of the rock, of the total rock volume, that give a good variability on the electrical logging response. And then we went for a very difficult parameter to measure, which is the water saturation. So basically, we actually at this moment we are using the dielectric as a main tool to measure the water saturation in Vaca Muerta. We use also NMR T1, T2 as a log. We try to do not use resistivity Archi-based equation, sigma nu or dual water, and we use with caution TRA and GRI, because we think that we are losing some water during the core extraction process from the well site to the lab. Looking at the resistivity of the lower Vaca Muerta, which is quite homogeneous zone in Vaca Muerta, we observed that there was a trend on the total resistivity or the average resistivity of the lower Vaca Muerta at the different maturity windows. The resistivity tends to go up and then start to comes down in the direction of the dry gas zone. This is what we call the resistivity reversal phenomenon. And this resistivity reversal phenomenon was also observed in US shale plays. The difference between Vaca Muerta and US shale plays is where the peaks of the very high resistivity appears. In Vaca Muerta, it appears in an immature stage, where in most of the US shales, it tends to appear in the dry gas window or in the wet gas window. We still don't know why it is different in the between the two peaks. Here we have a cross-section of the resistivity of Vaca Muerta, lower Vaca Muerta. In red colors, we can observe the high resistivity, and in blue, the low resistivity, and we can see the peak of the high resistivity located in the immature window. So we started to think about who can cause this resistivity decrease. We started to think about the possibility of thin lamination of pyrite. Actually, there is pyrite in Vaca Muerta, and we managed to observe horizontal thin layers of pyrite, which contain a very high conductivity. And also, we were capable to measure the weight percent in pyrite by using nuclear spectroscopy. Basically, we come up with the conclusion that the pyrite content, although we don't know from nuclear spectroscopy if that pyrite is laminated or disseminated, it seems to be that it's increasing towards the direction of the dry gas zone. But also we were capable to measure the amount of layers per meter of those pyrite veins. And we observed also that it was a big increase of those thin layers of pyrite towards the direction of the dry gas zone. So, because this is a horizontal resistivity measured by the induction logging tool, we think that the pyrite, even in a small amount, it could cause the decrease of the resistivity towards the dry gas zone. But we started to analyze as well some other information from the triaxial induction resistivity, which is also capable to measure not only the horizontal resistivity, but also the vertical resistivity. And we observed that the vertical resistivity as well is decreasing towards the direction of the dry gas zone, which would not, it won't be possible that the pyrite, because the direction of the pyrite lamination is horizontal, it shouldn't affect the vertical resistivity. So we started to think what it could cause this decrease of the vertical resistivity and how it affects our water saturation calculation. So we started to compare water saturation average results from different methods. We started to use this ARC equation or ARC-based equation. And obviously, we started to see that the water saturation, which is represented in the blue bars, tends to increase toward the dry gas zone because the resistivity is going down. But we started to think about other possibilities by measuring sigma from nuclear spectroscopy or the amount of water from NMR T1, T2, and also from the dielectrics. And we come up with the conclusion that only the resistivity tends to show that increase of water saturation towards the dry gas zone, but not the other techniques, which are completely independent techniques. So based on that, we have two answers here. The first one is that the decrease of resistivity do not reflect an increase of water saturation. Actually, the water saturation in the dry gas zone, it could be even lower compared to the oil window. Another thing that we come up is that we need to compensate in a certain way the calculation of the water saturation when we use the resistivity. We can use the resistivity, but we have to be cautious by using the resistivity to compute our water saturation. Finally, we went to the pore system characterization, which is quite difficult in this kind of environment because the different problems of scaling problems. Basically, so far, we are using an NMR T1, T2 to characterize the variability of the pore system, but also we include some other techniques from core in order to characterize the variability. Our idea in the future is to start with electronic microscopes images, and then pass through high frequency NMR, low frequency NMR, and finally make a proper upscaling to the electrical logging suite and NMR acquiring the vertical wells. This is our general idea, and this is a vertical well where we start to think about this variability on the pore space. We have the T1, T2 map. In the second track, we can observe the mineralogy, the passé crossover, and then we started to compare different volumes obtained from the core analysis against the volumes obtained from T1, T2 map using the blind source separation technique. First of all, we look at what we think is the gas field porosity, which are the biggest pores. Those pores they release the hydrocarbon, leaving an empty space of gas, and this is what we call the gas field porosity. And this have a very good correlation with actually the biggest pores obtained from the T1, T2 map. Then we compare what we think is the bitumen, and then we compare the water, clay bank water, and finally all hydrocarbons located in this zone of the T1, T2 map. One comment related to the water is that the amount of water obtained from the core was lower compared to the amount of water obtained by adding this volume on this zone of the map. And we think that this could be the effect of releasing water during the extraction process. We have other ways to prove that we lose some water when we took the core at the downhole and then we sent to the labs at the moment of the measurement. We think that we have lost some water. And there is another point here, is that the signal located in this area still is unknown. We don't know exactly what represents the signal located in this zone of the T1, T2 map. But basically, by doing this, we were capable to have a better idea where the fluids are located in the T1, T2 map, and observe, obviously, by doing that, observing the variability of this fluid distribution in the vertical direction, and start to look into this response in other vertical wells located in different portions of the basin. Finally, we went for the data analytics in order to understand a little bit more about the response of some fluids in the rock. Our main idea was to use the data analytics in order to see if we are capable to measure the amount of water by using different responses obtained from our petrophysical model. So our first guess was to say, well, if we characterize the mineralogy of the rock by nuclear spectroscopy, can we measure or can we get a correlation between the mineralogy and the amount of water obtained by the dielectric? Well, we went into the data analytics group in our company, and we gave the problem in order to be solved, and they found a variable in order to calculate the amount of water by using only the mineralogy, which is the blue curve here, which is a synthetic blue curve. And actually, in a well C, we were capable to get a very good correlation between the dielectric among the water from the dielectric, the water from NMR T1, T2, and also the synthetic that was obtained by using the this data analytic model. But it works very well in the well C, but it doesn't, or it didn't, in the well A. So that means that in certain zones of Vaca Muerta, it looks like the mineralogy, we'll say, has a strong correlation with the amount of water, but in other wells, that correlation is not even possible to define. There is more water than the model predicts, and this could be the effect of something else. Actually, we were capable to characterize the amount of water in this zone upper very well, very precisely with the data analytics, but not in the lower zone. And we think that it could be related to something else. So that amount of water, it doesn't come, or it's not related purely to the lithology, it's related to something else, like fractures, we don't know, or even faults or something, but actually it's in the matrix, and it's not related to purely to the mineralogy, at least on this well. Finally, as a summary, I want to summarize that the heterogeneity matters. It's important to consider the heterogeneity of the rock at all scales. Heavy oil components as well matter, especially when we are calibrating the core and the log in order to obtain porosity. And obviously, we have an effect in oil place estimation. We tend to do not use resistivity to calculate the water saturation. We prefer dielectric and NMR T1, T2. We are still calibrating this, but we think it's more reliable way to measure or to obtain the water saturation in Vaca Muerta. And finally, the pore system characterization will help us to predict the accumulated liquids, and actually to see by doing that we will be capable to see the variability of the pore system in a vertical direction, and obviously in a different position of the wells located in different position of the basin. So here are all the papers that they use in order to make this presentation. Some of them I was part of co-author, some of them not. I can share with you if you want. You have any question, you can read those papers. I want to thank YPF to give me the chance to present this data, and all my colleagues that helped me with this presentation, and also on the learning curve of Vaca Muerta, and my family that also is with me all the time. I want to just highlight the advantages of being a member of SPWLA. It's a great organization. I strongly recommend to join this organization. Has a lot of benefits, and there are very good activities that can be done in this great organization. And I want to invite you to the 61 annual symposium, SPWLA, which will be online because the problem of COVID-19. Well, thank you very much. Thank you very much, Javier and Catherine and Houston SPWLA chapter for the invitation, and I'm open for questions.
Yeah, Alberto, thank you for your presentation. Here we have a few questions. One is from Gary Simpson. Let's say, I think you will find that core measurements not matching logs is more a function of incomplete cleaning of the core material. Compare core NMR before cleaning to post cleaning will identify the error. Use T1, T2 on core measurements.
Well, that's a good point. Actually, we did. I couldn't show you that because it's not been published. But we'll say that we also did twin samples and compare the total porosity from TRA, GRI, and NMR. And actually, the porosity from NMR in plugs compare pretty well with the porosity from DINSTARC or from GRI. So, and actually, we did NMR post the extraction process, and the porosity was almost 0. So that means that the cleaning process of the de-extraction was okay. And actually give us more a better idea that we were in the right direction by using NMR to calculate the porosity. So the question is, yes, we did. We did NMR measurements after the DINSTARC process, and the porosity from NMR was almost the same as the DINSTARC, adding the gas seal porosity as well, of course. What we think is that in complete, release of what we think by using TRA in rocks, in immature rocks, we think a TRA is not being capable to remove heavy oil components or C20 plus. And those components are having effect on the total porosity that we measure with the TRA.
Okay. So next one from Sebastian Ramiro Ramirez. Have you conducted any permeability measurement? Have you observed any significant permeability differences between lithologies?
Well, that's a good question. Yes, we did we tried different permeability measurements. We use steady state, unsteady state, pressure decay, pressure decay is unsteady state, pressure decay, pulse decay, step decay permeabilities, and we measure them. We don't have any conclusion at all. We don't think actually we can trust on the permeability measurement in this kind of rock, either by the problem of identifying fractures that it could increase the permeability, and we don't know if those fractures actually present downhole, and the problem of removing the liquid properly in the rock in order to do a proper measurement of permeability. So the answer is yes, we did. We did a lot of measurements of permeability in core. We still don't have any answer about if the permeability is real or not.
So another question here from Mohamed Muhyiddin. What are the advantages of Raman maturity over other methods?
Well, that's a good question. Yeah, the advantage is that the main one is that the vitrine reflectance is quite easy and simple to do, but is human dependent. And we have a very lack of material because it's a marine environment. We have a very lack of material in order to get a proper measurement of vitrine reflectance. Our histogram on the vitrine reflectance shows that we have very uncertain data. And Raman maturity gives us more confidence on the results because we can do many more measurements even in one well. Another advantage against the other methods is that the pyrolysis is a very good indicator of maturity, but in immature rock or early oil window, when the rock releases a lot of hydrogen content or hydrogen index decrease quite a bit, either T2, either Tmax, or either the hydrogen index is not being reliable. So I think with the Raman maturity is the only technique that is capable to measure properly the maturity in I will say in the vitrine reflectance of more than 1.5. I mean, in a very mature rock, I think Raman is the best technique to be used compared to the other ones.
Okay, there is one last question here. Does the depth trend from Raman measurements match any depth trend from other RO measurements?
Well, we are in a process to analyze that. Yes, it follows other trends that we were observing in Vaca Muerta. Yes, indeed, it follows. But we need to just take into account that the Raman, as I said before, the Raman maturity tends to be more affected by the solid part of the rock. So we are observing the trend or the changes in the maturity on the solid part of the rock, which is represented by the kerogen. We still don't know about the fluids, but actually, when we compare, I will say the Raman maturity changes over depth against the inversion or maturity inversion that we got from the electrical logging. They follow the same trend, a very close trend. Unfortunately, we still don't have the results. We didn't have a chance to compare in the same well in order to show that that variability in the same well, but they follow the inversion maturity from electrical logging against Raman maturity. They follow the same trend. Yes.
Okay. So there are several questions here. It's a very interesting topic, but unfortunately we ran out of time. So apologies for not going through them. Feel free to contact Alberto directly. We are recording this presentation, and we will share it with you. The slide pack is also available from Alberto. So thank you all for attending today, and thank you, Alberto, for a huge effort in preparing this presentation for all our members. Really appreciate, SPWLA is possible because of the volunteers such as you, and thank you again for this effort, and also to all our audience. Thank you for attending, and best to you. Thank you.
Thank you very much. Thank you, Javier. Thank you, Catherine and Katharina and Houston chapter for inviting me to make this presentation. And thank you the audience as well, for sure.